All right, there you go. All right, let me pull this back up. So our graph, here's x-axis, y-axis. I solved that incorrectly, so don't look at that just yet. 4, so our y-intercept would be a 4. And a slope of a -1/2. We don't really need to extend beyond the first quadrant. And in fact, I would recommend not. It'll just confuse you. So that we ultimately kind of finish right here. So that's our general shape. So this is our area. So I could have asked you this question yesterday. Give me the area enclosed by this curve, this line, and the x-axis. That was our quiz yesterday. Now what we're doing is we're going to put something on top of that. And we're going to give it a height. Now it's going to be a third dimension. That's why we're going to be dealing with a volume. So in this case, it says the cross sections of the solid. And then what I have here is important. And it won't always be italicized, underlined, and in bold print. But whenever you do a cross-section question, this is important. Perpendicular to the x-axis, we know the x-axis is horizontal. Perpendicular means we're going to put these in vertically. Because when do we use the x variable? When do we use the y variable that we talked a little bit about with our quiz yesterday? Same thing with these. So I'm going to take a semicircle. So let me do this in red. So think about a circle. I'm going to cut that in half. So we're just going to be dealing with a semicircle. And we're going to take that semicircle and we're going to take its diameter and place it on the xy plane. So here is its diameter. So remember the little diagram that I just showed you. We're looking at it from directly on. That's what we're looking at on our paper. But from the right-hand side, when we got a bit of an angle, we can see that it's a triangle. So as best you can, draw in a semicircle. So I'm going to kind of do it here. That's really bad. Actually, not a bad drawer of these things on the board over the year. And then draw a few more. So draw a semicircle here, and then here. If we stack them directly on top of each other, smash them all together, then it's a nice continuous solid shape. But just draw in a couple so that we can visually kind of see what's going on. The reason I drew them in vertically is because of this idea, perpendicular to the x-axis. If I had said horizontally, we're putting those in as horizontal circles, or semicircles. All right, then it says, what is the volume of this solid? So here's what we now do to set this up. What we know is the area of a semicircle is always 1/2 pi r squared. Well, if we look at these semicircles, they're not an area, right? It's impossible for a cross-section to be an area. The width of this, doesn't this have to have a width basically as long as my ink pen? All right, my computer pen here. So whatever this is and this is right here, that's the width of my circular disc. So if we then give it a width, which it would have to have, or it's not a cross-section at all, we can't take a flat anything and put it as a cross-section because you're implying when it's flat there is no width to it. If we give it a width, we're now dealing with the idea of a volume. I have 3 of them drawn in. What we again would ultimately have, and that little computer generated one that I showed you with triangles shows them, is we keep adding more and more in there. They get smashed on top of each other. We want to add them all together. So we don't just want one, we want all of these guys. So if I want the volume of the entire shape, I don't want the volume of one single semicircle. I want to add them all up. And that's what the definite integral does for us, because we, again, don't want to necessarily go backwards and revisit Riemann sums. The definite integral will add all of them for us. So when we now go to set this up, what we're really just adding is the area of a square, or sorry, of a semicircle that have a width to it. That's why it's a cross section. And we're going to add them all up using our integral over whatever interval we're going to be going from. So when we now go to set this up in a way that's going to allow us to answer this question, I'm going to pull out the 1/2. I'm going to pull out the pi because they're constants. We'll get our limits in a moment. We then need to define our radius. So if we look at this, notice how the radius of all these circles is going to be different. They don't have a constant radius, so we're going to have to define this algebraically with a variable because it's constantly changing. So this will be 1/2 times pi r squared. And then like I tried to show here, the width of all of these is my pen. So isn't the width, if I look at my red ink pen, see how that's lining up against the x-axis? So whatever the width along the x-axis is, that's going to be my width. So here to here, whatever that would be. So that's why we're going to call this our change in x. This is in terms of dx. So anything, again, vertical is going to be done with respect to x. All right, our change in x. Draw a radius into your best circle. So this is probably my best circle right here because there's some pretty bad circles. That's the radius of my circle there. Make this even bigger because it's kind of hard to see. If I draw in a radius to my next best right here, that's the radius here. So like I said, these are all different. So that's why we need to use a variable to define these. So it's similar in respect to what we just quizzed on. If I wanted to know what is the radius of this circle here, aren't all of these radii bordered by the exact same curve on the top? So it always is going to boil down to some point, top minus bottom, right minus left, just like we just quizzed on. So if I'm going to define the radius of this semicircle, the top curve is this y equals a negative 1/2 x plus a 4. Minus, and then our issue with this type, which is a common issue, is there a curve bordering our radius on the bottom? Is the bottom of the radius touching a curve at all? No, it's just floating out in space. It's not bordered by anything. So what's a really, really common thing for us to do, because we're going to be dealing with a lot of circles and semicircular cross sections, is we're going to be able to, instead of defining our radius, have to define our diameter first. Because if I extend this now all the way down my circle, don't each diameter now have both a top and a bottom function that they're bordered by? Yes. So that line is on top, the x-axis is on the bottom, so that's the equation y equals 0. So again, this is our top minus the bottom, but now we're doing that for our diameter. So that's how we can define that using algebra. We know, though, ultimately what we need is a radius, correct? We don't want a diameter. So our diameter would be that expression. Give me myself enough room there. Let me do it. My radius then would have to be that expression that we just defined as the diameter cut in half. This then is what we throw into our integral. So this is going to become a negative 1/4 x plus 2. That would define the radius of any semicircular cross section that I have drawn into this figure. And then we would want to know, where do our circles start getting drawn in at? Our first circle would have started right here. This would have been our biggest circle. That pretty clearly starts at the x value of 0. And then we would have continued to smash semicircles in. So here we go, smashing them in there until we get to the very bottom, whenever we would have crossed the x-axis right here. So we would need to figure out what is that x-intercept. It's really nothing more. Think of the x-axis as y equals 0. Where does this line and this line intersect? So same stuff yesterday that you probably did a few times just in terms of the algebra. Set those equal to each other, solve that equation. I do that in your head if you'd like. Oops, positive 1/2 x. And we should get them to intersect at 8. So we would be smashing all of these semicircles with this radius starting at 0 through 8. Okay? So it's nothing more than the sum, that's what the integral is, starting at 0 to 8 of 1/2 pi r squared. So that's our circles with an area, but each of them has that infinitely tiny little width. And that's why it ultimately is a volume. Okay? At this point, calculator, you throw that in. We should be pretty efficient with math 9. We're just going to go through, set all these up real quick to save a little bit of time. Although I would be careful, don't forget the squared. That's a really, really common mistake. I guarantee you that's going to be one of the distracting answers when it becomes multiple choice, because people forget to square everything very, very commonly. Actually, go ahead and throw that in, I suppose. It's our first one. You want to decide, how do you want to handle the half out in front? I don't have my graphing calculator up. It takes like 10 minutes for this thing to open. If you want to put 1/2 pi and then math 9, you could. If you want to just do math 9, don't forget to multiply by that 1/2 at the end. It's really sort of up to you. Come on. So throw that in there. See what we get. This takes a while. I don't know why it takes so long for this to open. Also understand, when you square something in your calculator, you got to open up your own parentheses. The initial parentheses that the integral opens cannot be squared. So you need to open up your own parentheses right off the bat. Jeez. All right, that only took 3 minutes. Still not up. All right, and then it depends. Sometimes I'll want it as a decimal. Sometimes I'll want it as an exact answer. Exact answer. Yeah, so I didn't put the 1/2, so I'm just going to go 0 to 8. Because I know I'm going to have to square everything, I need to open up my parentheses. I'm going to do this as a decimal. Instead of a -1/4, I'm going to -0.25. Fractions just create more issues in terms of order of operations sometimes. And then x squared, what was it, +4? Is that right?
+2.
+2. And then I can close that, now I can square it. Keep in mind, I did not multiply by 1/2, that's why that doesn't look right. What is that? Oh, that's it? Okay, good. Thank you. Oh yeah, because it's a line. All right, let's try this again. That was awfully large. All right, so I get what? 32/3. We want to divide that by 1/2. So it's 16/3 pi. Typically, you're going to be asked to give the exact answer. So that would be 16 pi over 3. If you go ahead and multiply by pi, if it's optional, then make sure we go to that third decimal place. Okay. All right, that hopefully makes some sense. Any questions on that whole setup? That being our first one. We will kind of speed this up in a little bit, but that's kind of the premise of this whole thing, is the idea we're adding up a bunch of these cross sections, and whatever shape we're dealing with, square or circles, we'll define those segments using the curves in play. All right, so 2. All right, so the solid lies between planes that are perpendicular to the x-axis at x equals a -1, 1. The cross sections, and again, our cross sections are going to be perpendicular to the x-axis. That means they're vertical. Between these planes are bordered by that circle. So draw in that circle first. And our radius is just 1. So we know there's 1s all around here. So like I mentioned yesterday, we would just be concerned about this flat space, like how much flat space are we taking up on our paper or floor or wherever this is at, my computer. Now we're going to create a depth. We're going to create something by putting something on top of it. So what we're going to put into this figure now, our cross sections are going to be circular discs. So think about a circle. We're going to put their diameters in the XY plane. So what that means, this is a different color. Think about a circle. Think if I could pinch that, if I could grab this and move it, I'm going to put the diameter of this circle in the XY plane. So that means the diameter is touching the top and the bottom, the top of the circle and the bottom of the circle, in a way that half of the circle is in front, half of the circle is behind. If we're really understanding this whole cross sections as circles, you would be thinking, isn't this really just a sphere, correct? We're understanding that. Okay. So geometry-wise, we could do this one with geometry, right? 4/3 pi r cubed is the volume of a sphere. The radius of this sphere is 1. So this answer using calculus better give us 4/3 pi. Has to, using an integral. Now, not all of them we can use a geometry shape. That's why we want to have this method for now anything. But we can do a little geometry calculus to reinforce that our answer should be 4/3 pi. So the way we now set this up, the way we always want to kind of understand it is, what is the area of our cross section? In this case, our cross sections are circles. So that's now a regular old pi r squared without the half in front of it. But each of those circles, in order for it to actually be a cross section, has to have some sort of a width. That's why we're really dealing with a volume. This would give us the volume of just one circular disc. We don't want the volume of just one circular disc. We want the volume of the entire shape. So if I were to do the sum of all of them from A to B, integrating pi r squared times our width, that would give us the volume of the entire shape. So when we now go to set this up, I'm going to pull the pi out. Our radius for all these circles are going to be different, so I'm going to have to define my r in terms of variables. The width of all of these, so if I actually drew a diameter, notice how I didn't actually draw a diameter or a radius in here, right through here, notice how it's crossing right through the x-axis? Well, that's its width, is along the x-axis. So the width of each of these would be defined as our change in x, so that's going to be dx. Now take a circle or two, draw in, since we're trying to define a radius, just like we did before, draw in a radius to one or two of your circles. I have 3, so I'll draw in all 3. Now if I look at those radii, those 3, so this guy right here, notice how I do have something bordering the radius on top, and I do have something bordering the radius on the bottom. So I can right away define that length by doing the top curve minus the bottom curve. We don't have to worry about a diameter getting cut in half. So we want to go ahead and do top curve minus bottom curve. Your issue though is we need to make sure everything is in terms of x. So the way this is written, we're going to have to do a little algebra here real quick. Solve that for y. So y equals 1 minus x squared. Take the square root. So y equals the positive and negative curve for root 1 minus x squared. That's important, the positive and negative in this case, because the top half of this circle is defined as the positive y values, so the positive radical. The bottom half of that curve gives us all the negative y values, so that's the negative root 1 minus x squared. So when we now go to define our radius, here's the radius I'm going to define. Isn't it pretty clearly bordered on top by the positive radical? So I'm going to do the top curve minus the bottom curve, and it's bordered on the bottom by the x-axis, which is y equals 0. And our limit, since we're doing everything in terms of x, we start at the x value of a -1. We smash all these circles in until a +1, so we go from a -1 to 1. I promise you, if you threw that into your calculator, it is going to give you 4/3 pi, which is the same thing we would get if we just use the volume of a sphere. All right. All right, B. Start a little quicker here. Draw the circle again. Same exact circle, radius of 1, 1, -1, 1. Now we want squares to be our cross sections. So same idea in terms of, this is probably the hardest one to draw in, at least for me. Think about a square. So pretend that all sides there are the same. I'm gonna, if I could grab this, like say I had a tool or I could actually grab that, I'm gonna place this side of the square onto this circle. So I'm gonna take this side, it's gonna land on top of this. So in 2 dimensions, it looks like this. But understand the rest of this, if you think about your piece of paper on your desk, that's gonna be sticking up. So as best you can, try to sketch in what that would look like. So I'm gonna draw it like that. We know the area of a square. We could say base times height, but in Calc, right now, Calc 1, you just want single variables. So instead of base times height, we're going to define it as side squared. If we know that each one of those is not just a flat square, each one of those squares has a bit of a width to it. That's why it's a volume. Since we want all of them, not just one of them, then the integral will do that for us. But each side is going to be a different length, so we have to define that. Let me draw another square in just to make sure we understand. And each side of the square is going to be different. Our biggest square would be right down the middle. Our smallest ones would be occurring at the end. So different sizes of sides. Notice how my red ink pen is going right through the x-axis. That would be the width of all of them. So that's why we know vertically our width is going to be the dx. Now I need to define a side. So if I look at this side right here, I need this whole entire side. I need this whole entire side. Do those sides clearly have a defined top curve and a bottom curve that are bordering that side? Yes, okay. So if I look, isn't the top curve here the positive radical? And then we come all the way down, I'm defining this side right here. The negative square root curve is the bottom. So if I probably didn't leave myself enough room with this giant writing. So we want the positive radical root 1 minus x squared minus the negative root 1 minus x squared. Limits are still negative 1 to 1. So now, it's up to you, and this is really messy, so let me try to clean this up. To plug this into your calculator is a little messy with all these square roots in there. So it's really up to you, kind of where do you want to spend your time. You could simplify this a little bit. You could certainly plug it in right now. This is just messy to plug into your calculator. We could, obviously we're going to add these. You could do 2 root 1 minus x squared. This is a little bit easier to plug into your calculator. So you can plug that in if you want. This actually simplifies a little bit more to be 4 times 1 minus x squared. And then our dx. Uh-oh. And then if you want the absolute easiest thing to plug into your calculator, then this is hard to mess up, 4 minus 4x squared. So it's really where do you want to spend your time. This is harder to plug into the calculator. You'll spend a little more time plugging that in and making sure format is correct. Do you want to go through the work to clean it all up? This is super easy to plug into the calculator. Totally up to you. All right, as long as you numerically get the correct answer, it does not matter. Okay? Okay, good with that? Okay, I'm going to plug that in so I can give you the answer. Somebody already has done it. I'm going to do that one because it's super quick and easy. But if we go to C, try to sketch this one in to see what we get, and I'll throw this in. So your same exact curve. So this is once again the positive root 1 minus x squared. Down here is the negative root 1 minus x squared. You're going to draw in triangles. See, equilateral triangle also. There's a special formula so that we can stay in one variable. That's root 3 over 4 sides squared. That's the area of an equilateral triangle. 4 minus 4x squared. Okay, and letter C, you should get 16 thirds. So if you plug that in, whichever version you plugged in, the complicated one or the easy one, all right, that's our answer, okay? All right, C. So here's our area. What you're drawing in is an equilateral triangle, so I'll sketch it over here. Pretend this is equilateral. I'm going to place this side right here. This is actually similar to the one that I showed you with the GeoGebra site, where if this is my triangle, the base of it, the vertex is pointing up towards us. So it would look kind of like this. And then our biggest one is right down the middle. Smallest ones would be on the end, so on and so forth. So this actually would, if we were to do it again, look like that version that we were looking at the beginning of class. So same process. Here's the area of our cross-section. Cross-sections cannot be flat. So if they have a width, that's why we're talking volume. And if we want the volume of all of them, you're going to add them all up. So I'm going to put the root 3 over 4 out in front. We need to define the length of the side. The width, look how my marker is going through the x-axis. So the width of my marker is currently our change in x. See if we can now define the side that we need to define that's laying on the circle. This is hopefully really, really, really easy. And it's hopefully really, really easy because it should be very, very similar to the previous question, correct? As in the exact same thing. So if I were to look at this side right here, it's bordered on top by the positive radical, on the bottom by the negative. Same with this one, same with this one. Any one that we would have drawn in there, no matter where you drew yours in, the positive square root curve is on top. and the negative square root curve is on the bottom. Okay. Limit still negative 1 to 1. This is really easy. I don't need to use my calculator because we already know what this integral gives us, right? That's the one that we just plugged in the previous question. That's going to spit out a 16/3. Now we just have an extra root 3 over 4 out in front. So that's what, 4 root 3 over 3. All right. What do we got? All right, let's try to get one more done here. The next one I think is a calculator question. You'll definitely need your calculator, so pull that out. If you haven't already. So it says solid lies between the planes perpendicular to the x-axis, negative pi over 3 to pi over 3. We're still going to be perpendicular to the x-axis. You're going to have circular disk. The diameters are going to run from the curve tangent of x to the secant of x. Graph these real quick. Tangent, you may have an idea of what that looks like. Secants, you maybe have a really foggy idea of what that looked like. So you probably want to use your calculator to graph these. This is certainly a calculator question. Then if you remember, so as you hit and secant is 1 over cosine, so make sure we understand that. When you hit that graph button, it's a mess, right? You got all kinds of stuff going on there. So that's why we want to make sure we're able to manipulate our window a little bit. Depending on what set of questions you had yesterday, you certainly had to do that for one of them in particular. So we probably want to change our window, negative pi over 3 to pi over 3. But with that, now think negative pi over 3 is really about a negative 1, and pi over 3 is really just a positive 1-ish, all right? If you keep your 10 by 10 window vertically, now your window is a 2 by 20 window. So now it's still very, very distorted. So I would also kind of shrink down your y-axis as well. I think 2s or 3s would probably work reasonably well. And you take a really ugly, messy graph that the two curves would give you. And if we do it with the right window, then it's pretty straightforward. So we have our cube graph, or not, it looks like a cube graph, which is the tangent graph, should look like this. And then you have your secant graph in this window, looks like this. And then we're only going from a negative pi over 3 to a positive pi over 3. And if you've changed their window in the calculator, this should be pretty much what you're looking at right now. We're just zoned in now on the important stuff within the interval that I ask you to work with. So we're bounded on the left by this imaginary vertical line at pi over 3, and then these guys hit at pi over 3. From there, draw in your circles. We are still perpendicular to the x-axis, so that means we're just drawing these in vertically. So draw in circles so that the diameter is in the xy plane. So all that really means is half the circle is in front, half the circle is behind. So our tiniest circles are at the top, our biggest circle is at the bottom. So it's kind of like a horn of plenty from Thanksgiving. All right, it's solid and it gets bigger and bigger and bigger. From there, area of each one of these, it's a circle, is pi r squared. Our volume is each one of those circles having a width to them. And our overall volume is the sum of all of those. And we're still vertical, so our width would still be the change along the x-axis. Limits don't get any easier. We're going from negative pi over 3 to pi over 3. That's where the first disk would have gotten drawn in. We smash them all the way to the positive pi over 3. So to wrap up class, maybe I don't want to leave you too much time. We need to define our radius. So if I draw in our radius right here for any of these circles, we are back to the first problem we did. It's probably the most common AP question because it's the trickiest, quote unquote, trickiest one. Because if I now try to define my radius, we have a top curve for every radius in here. but every bottom of every radius is just kind of hanging out into space. It's not bordered by anything. So it's one of the ones where we can't define our radius right away. However, we can define the diameter. So if we actually extend this all the way and draw the diameter of our circles in instead, we now can do the top and the bottom, and then we just need to cut that in half to get the radius. We should hopefully know, well, you have your calculator, so that would tell you, but we'd hopefully know the tangent curve looks like the x cubed graph. So that means secant has to be on top of every diameter. The tangent is on the bottom of every diameter. Since our equation calls for a radius, we just take that expression, cut it in half. And then that's our guy. This you just had to set up. You didn't have to evaluate it. So then this would be our final answer for this one. Okay. Bring this tomorrow. We may skip 4 altogether. I definitely want you to see the 2 that where I have you perpendicular to the y-axis when they go horizontal. Okay. So we'll finish this tomorrow. We'll see where we're at, and we'll definitely get started on that next set of notes. Okay. And we'll probably go over the quiz as well. Okay, that's it. We got less than a minute. All right, we'll see you guys. Have a good night. We'll see you tomorrow. Oh.